So I feel like I should do a bit of a recap because this is the last of the word problems. And so the word problems that we've done so far, we did a little bit of an intro to them where they were so easy you barely needed my strategies and it was probably more of a pain. We did the percent problems where you always put 100 down below and the percentage and the amount and the base, right, as a setup. Then we did the consecutive integer ones. And those ones always had the same let statement. So it was x, x plus 1, x plus 2, or for the odd or the even, it was x and x plus 2 stuff going on. After we did the consecutive integer problems, we did the total of, or the sum. And really in those ones, it was translating. And it was translating your let statements. That was really the key bit to those ones. After that, we did one of my favorites, which is the geometry ones. And you had two pieces of information. You had a picture that you drew, and then you had the framework equations. And those ones came off of your formula sheets or your textbook. They're at your disposal. You don't need to have those ones memorized. Then the last ones that we did were the mixture problems. And that's where we had the different boxes going together to build an equation that we read off the bottom of those ones. And the last ones are motion problems or distance, rate, time problems, or sometimes called the DRT problems. I know that's not how you spell dirt, but that's what people call them. So anyway, these are the last kind, and we're going to start off with these ones because with all of these, you have some level of intuition. If you go at 100 kilometers an hour and you travel that fast for 3 hours, how far did you go? If you said 300 kilometers, you are right, because what you know is the general equation for distance, rate, and time. You know that the distance traveled equals the rate times the time interval that you have to travel. And so what's going on between these two is multiplication. And this is the keystone sort of formula for distance, rate, time. This is what we're going to use. And you already know it if you know this sort of concept. In these ones, we're going to draw a little diagram that illustrates the motion. And I'm going to fill those ones out down below because there's 4 different kinds that we're going to do. We're going to fill in a chart with the let statements because all of these are going to be in a DRT chart where we have a distance 1 and a distance 2, and distance always equals rate times time. So I'll do more about these charts as we move through the different kinds of problems, but this is the basics of the chart. So maybe this is the trip to the beach, and this is the trip home, right? Or maybe this is the distance you travel, and this is your friend, right? We're going to have different scenarios with these, which I'll outline, but this is really the key to them is this chart. And the chart, as with the other charts, is a way to represent your let statements, and it's also a way to build your equation. We're going to build our equation from that chart and then solve. And there are 4 different sort of ways of looking at motion problems, and I'm going to fill those out here. So this idea that we have this distance, rate, time, I'm just going to put that again closer so I don't have to scroll for it. You probably still have it. So distance 1, distance 2, and we always know that distance equals rate times time. So these idea of pictures for these, I think helps. And so this first one is the return trip. So the return trip says that you leave from Nelson and drive to Castlegar, and then you're going to leave from Castlegar and drive back to Nelson. Now, nothing changes in the distance traveled, right? It's the same distance, but it might take you longer and you might go slower getting there than it does coming back. So your rate and your time might be different variables, but the distances are going to be fixed. And so this would be the picture that illustrates the return trip. And the framework for the formula is that you would have distance 1 equaling distance 2. And we know that distance 1 is this rate times this time. And we know that distance 2 is this rate times this time. So in that way, this is the framework that we would use for that return trip. So let's think about catching up. So this is you leaving on your bike, biking to Balfour, and this is your friend who takes pity on you because there's a massive windstorm and is going to catch up to you in the car. So this would be the bike and this would be the car. Now, the bike's going to go slower and it's going to take longer, and the car is going to go faster and not take as long. But the two distances, if your friend does indeed catch up to you, will be the same. So again, the framework of these would be distance 1 equals distance 2. And from drawing the picture, you can see that relationship, I think. And so that's the idea behind this sort of analysis of these distance rate time problems. So there's two more. So this moving away business. So this is you and your friend, and you are going to go north to Caslow, and your friend is going to go south to Selmo. And so this would be your distance traveled. This would be your friend's distance traveled. So if we are talking Caslow to Selmo here, there is a fixed distance. There is a total distance that these two are apart. And that's something you could look up or be given in these questions you're given. So this idea of a framework and building from our chart to our equation is that in this case, distance 1 plus distance 2 equals whatever that total is. And that's what gives me the framework to go from my chart to my equation. So the moving towards, so this is you leaving Caslow, coming towards Nelson, going whatever speed, and this is your friend leaving Selmo, coming towards you. Again, this would be distance 1. Your friend could be distance 2. And again, there is a fixed distance between those two locations. And so this total of them coming towards would give me a framework where distance 1 and distance 2 added together would give me a total. So your cue on these ones, if you're given a total, it would be these two scenarios here. If you're not given a total, it's these two scenarios. So we're going to go through two examples of each of the scenarios. I'm quite sure that usually after the first one, you've got them, but we're going to take our time and go through these. Okay, so these ones are lovingly labeled as which kind they are, which is helpful. And this one says that on Friday, Ricardo drove from his house to the beach in 4 hours, and coming back, he's slowed by 10 kilometers an hour, and his trip then takes 5 hours. How fast was he going in both directions? So this is a distance, rate, time problem. So I start off by recognizing that and drawing out my chart. The idea that we're going to have distance 1 is that this is to the beach. Distance 2 is coming home from the beach. And because this is a return trip, whatever expression I have for distance 1 equals distance 2. So let's see what other pieces of information can be filled out from the question. So it goes from his house to the beach in 4 hours. So that would be the time, not the time o'clock, the time interval, how many hours, for him to go from home to the beach. Coming back, his speed is slowed by 10 kilometers an hour, and now it's going to take 5 hours to come back. So we don't know what his speed is, but we do know that his speed here is reduced by 10 kilometers an hour. So coming up with the let statements, we don't know what it is to the beach, his rate is to the beach, but we do know that his rate is 10 kilometers an hour slower when he's coming home. So x minus 10 would be our expression for his rate when he's coming home. So now we know that distance 1 is rate times time. And so I'm starting over here. Distance 1 will equal distance 2. I should have put it at the top so I could build it up. So distance 1 is 4 times x because it's rate times time, or I'd put them in an order that made sense. And this one would be rate times time, or 5 times x minus 10. So now I've got my let statements and I've also got my equation. I'm going to distribute that 5 across. So I'd have 4x equaling 5x minus 50. Subtract 5x from both sides. I get negative x equaling negative 50, or divide by -1 on both sides, and I get x equaling 50. So that tells me that his rate to the beach was 50 kilometers an hour, and his rate to home is 10 kilometers an hour slower than that, so 40 kilometers an hour. So let's practice doing another one of these. It's still a return trip, but even getting some familiarity with the chart and filling that out, as soon as it's a motion problem, they all fit this DRT chart. So this question is about a plane, and it's going to go between two cities. So it's going to go with the wind and then turn around and go against the wind. We know that the distance 1 and the distance 2 are not going to change. The distance between the towns do not change. So distance 1 will equal distance 2. I'll put that framework at the top so I can better build that up. Let's put some information in here. So we know that the flight with the wind takes 2 hours. Returning, the plane's speed is slowed by 60 miles an hour and now takes 3 hours. So whatever his rate was before, it's now slowed by 60 miles an hour. I've got my let statements now filled into the chart, and now I use my chart to build my equation. So I've got rate times time for my distance 1, so that would be 2x. And my distance 2 would be 3 times x minus 60. I write them in a different order because that makes more sense to me, but it's still the rate times the time. I've got my equation now, and now I need to solve it. So distributive property is what I'm going to do first. And I get that his x is 180. So that is his rate with the wind is 180 miles per hour. And against the wind, that headwind slows him down. He's going to go 60 miles an hour slower. So it's 120 miles an hour against the wind. So there's 2 that are return trips. We're going to switch it up, and now we're going to do some moving away. So it says that it's a moving away, which is always handy when it's titled, but it's still going to be a distance rate time problem. So let's see how that looks when we pull out what we know from the question. So it says here, at noon, a jogger leaves one point running at 8 miles an hour. Okay, so we know this is going to be 8 miles an hour. An hour later, a bicyclist, so this is a runner, and this one's going to be a biker. So it says he's traveling or she's traveling at 20 miles an hour. So my runner is going to be distance 1, my biker is going to be distance 2. And the time, let's see what I've got about this one. So it says, so the jogger leaves at noon. So noon is 12 o'clock. That is not a time interval. So I can't put 12 down here in my time. So it does say over here that an hour later the bicyclist leaves. So I don't know how long the runner has to run, but I do know that the biker leaving an hour later has 1 hour less to travel. So this one is saying at what point, when will they be 36 miles apart? So we've got a total of 36 miles. Well, every time you're given a total, that means that your framework is going to be D1 plus D2 equals that total. So my D1 is that 8 miles an hour times however long the runner has to run, and the biker 20 times x minus 1 because he has 1 hour less, and it's 36 miles as the total. Okay, so let's solve this one. We've got our equation. Let's solve this one. 8x plus 20x minus 20 equaling 36. So when I get down to what x equals, it equals 2. So that tells me that there are 2 hours for the runner to run and 1 hour for the biker to run. But it doesn't say, how long do they each run and bike for? It says, when will they be that far apart? So in 2 hours, or because it says at 12 o'clock, at 2 p.m., they'll be 36 miles apart. And you can keep writing that sentence if you want. If it gives you an o'clock in the question, you can answer with an o'clock in your answer. If it doesn't tell you what time on the clock, then you can't add this one in. Both of these are correct, and it's probably best to give both if you can. Okay, so let's do another one. It says car leaves a city and goes north. So he's going north. And another one leaves and goes south. Okay, so that's D1. This is D2. Let's put this in a chart. I like the pictures, but the chart usually does it for me. Okay, so this one's going north. This one's going south. It's going to build up a D1. This one's going to build up a D2. So it's 50 kilometers an hour at 2 o'clock. And again, that's an o'clock, right? It doesn't go in the chart. Again, this T is a time interval. It does say then that an hour later, another car leaves that city and travels south at 40 kilometers an hour. So this one has X hours to travel. Again, this hour later means that this one's going to have 1 hour less to travel. And again, it says at what point will the cars be 320 kilometers apart? And so because it gives me a total, that tells me that the framework is that it's the sum of these two distances traveled. So distance 1 as an expression is 50 times x, and distance 2 is 40 times x minus 1, and that adds up to 320. So I've got my let expressions, I've got my equation, now I need to solve it. Distributive property is first. Going to gather up my like x terms. And eventually I get down to x equaling 4. And I could answer this one much like the last one. So in 4 hours or at 6 p.m. they will be 320 kilometers apart. I really went the distance on that answer. I don't know why. Usually I'm pretty brief on those ones. Okay, so catching up. I know it's different because there's a heading here. Let's see how these ones go. So it's a distance rate time problem, DRT. You can look back to the chart and take a look at the framework because it says catching up, or you can read the question. So it says Catherine, we got Catherine and we've got Max here as the two questions. She's leaving on a trip at 40 and going 45 miles an hour. Max decides to join her and travel along the same route at 54. Boy, this is a number switcher's nightmare. Sorry for that. When will Max catch up with Catherine? Well, in this one, oh, it does say an hour later. I was like, where is that? So she has X amount of time to travel. He has this X minus 1 because he has 1 hour less because it takes him an hour to decide to go catch and chase Catherine. Okay, so in this one, in this catching up, it's this idea that they have to travel the same distance in order to catch up. And so distance always equals rate times time. So Catherine would be over here, 45 times x, and Max would be 54 times x minus 1. I've now got my equation to solve. Distributive property is first. I'm going to gather up my like terms. When I get down to it, I get that x equals 6. So in 6 hours, or at 2 p.m., because that would be 6 hours after 8 a.m., Max will catch Catherine. You're probably starting to see some of the commonalities in these ones. Even though they're different scenarios, our approach to them is really, really similar. So the next one, a distance, rate, time problem. We've got Martina bicycling and then John driving. So this one's going to be bike on the top and car on the bottom. We're going to build up expressions for D1 and D2. So she leaves at 9 a.m. going at 24 miles an hour. And 2 hours later, so he gets x minus 2, John goes at 48 miles an hour. So what we're trying to figure out is how long until he catches her. So they should have traveled the same distance if they're going to catch up to each other. D1 is 24x and D2 is this 48 x minus 2. Distributive property working through here. We're going to gather up our like terms, subtracting 48x from both sides. Oops. Divide by negative 24. And I get 4. So again, that tells me that in 4 hours, or at 1 p.m., because that's 4 hours after 9, Martina, oops, sorry, no, it's John will catch Martina. All right, we're almost there. So we've got this last variation, this moving towards business. So we've got this idea that Baltimore and Boston are 425 miles apart, and one person is coming one way, one person is coming the other, and we want to know how long until those two people meet. So again, it's a distance, rate, time problem. So we can sort our information this way. We've got Micah and we've got Hiroko. And let's see what specifics we have. So we have a time o'clock, which we can come back to. And Micah is going at 45 miles an hour and has X amount of time to travel. Hiroko is going the opposite direction, this time going at 50 miles an hour and an hour later. So it's that X minus 1 business. How long until they meet? Because we're given a total 425, that means that our framework is D1 plus D2 would equal that total. And so my D1 expression is 45x and my D2 expression is 50 x minus 1, and that should equal the 425. We're going to do some distributive property, and we're going to collect up our like terms. We're going to add 50 to both sides. Divide both sides by 95. And I get that x equals 5. So that tells me in 5 hours or at, what is that, 3 p.m. One last, if you can handle it. One more in the word problems. So we've got train A leaving town. Sorry, let's try that again. A train leaves town A for town B, traveling at, let's just do the DRT chart. Okay, so 35. The same time, well, that's something different. At the same time, a second town leaves in the opposite direction, so they are definitely coming together. We're going to build up D1 and D2, and we've got a total of 320 in this one, right? Now, we have to decide, what do we do with at the same time? We're used to this 1 hour later, 2 hour. At the same time, they have the same amount of time to travel. So both of their time intervals is going to be the same. It's going to be X. So the framework would be the sum of my distances would equal the total. So D1 expression is 35x and D2 is 45x equaling 320. If I add these ones together, I'd get 80x equaling 320. Divide by 80, divide by 80, and I get x equaling 4. So that means because I wasn't given a time o'clock, the best I can do is say that in 4 hours, the trains will meet. All right, congratulations on the word problems. There's lots more to do, and if you want more on any of these, give me a shout, let me know. And congratulations, it's no small feat.